Yeah, yeah, thanks. Yeah, you can continue.
Okay. Hello, everyone. I'm reading from OpenMOS team, Shanghai Innovation Institute, and Fudan University. Thank you for having me here. Today I'm going to talk about our work on the field of mechanistic interpretability. The title of today's talk, which is also the one of our blog post, is Bridging the Attention Gap: Complete Replacement Models for Complete Circuit Tracing. My talk today will follow the roadmap. In the first part, Okay. In the first part, I'll focus on the main track of mechanistic interpretability. I'll first introduce some background of sparse dictionary learning and sparse autoencoder, or SAE. Along the way, I'll introduce our work, low-rank sparse attention, or LOSA. Then from feature to circuit, I'll further introduce our complete replacement model and complete circuit tracing. Then in the second part, I'll introduce two works of knowledge editing that builds from the idea of mechanistic interpretability, or SAE. Finally, we'll transition to and close with the current problem of SAE, which is dark matter and feature manifold. First, we have some background information. It's regarded that the neural network can encode many attributes in the data, which we called features, as the bottom right figure shows, such as red, left curving lines, or orthogonals, and the model processes them in a lower dimensional space compared to the number of features and use them to predict the output. There are three classic hypotheses about how features exist in the hidden space. The first one is the linear representation hypothesis, which means that features correspond to directions and can be linearly combined or operated. The second one is the sparsity hypothesis, which means that natural data can be represented by activating only a small number of features. And the third one is the superposition hypothesis, which means that features are non-orthogonal, allowing many more features than dimensions to be represented in the hidden space. In a way, the model learned a compressed low-dimensional version of the true model, where each neuron may correspond to multiple features. These three hypotheses naturally come together into the design of the architecture of sparse autoencoder, or SAE, enabling them to extract monosemantic features. A standard SAE consists of an encoder and decoder. The encoder maps the original activation into a much higher dimensional feature space, and the decoder reconstructs it back. During training, um, two laws are used. L2 reconstruction loss, and we use L1 sparsity loss on SAE latent to encourage sparsity. In classical SAEs, the activation function is ReLU, and it can be replaced with top K or jump ReLU to encourage sparsity. As shown in the upper right figure, building from SAEs, transcoders read from one layer and predict the output of the layer instead of reconstructing the input itself. Here, the two figures below shows the space of SAE decoders, and we can see that these features form certain geometric structures, like autoimmunity, legal and social immunity, and so on. And similar features may be located close to each other. The figure on bottom right shows how we can interpret a feature. For example, we can look at the top activations, which are the data that activate the feature most. And through directly mapping its decoder vector with unembedding matrix, we can see its negative logits and positive logits and its related neurons or features. Overall, SAEs are now widely regarded in mechanistic interpretability field due to its scalable and unsupervised learning method. And while SAE can be used to interpret the residual stream in the upper left figure, Transcoders can be used to interpret the MLP computations. Meanwhile, Anthropic also mentioned that attention head superposition. That is, most attention heads are hard to interpret individually, and they verify that attention output SAE features are collectively computed by multiple original heads. For example, in the right figure, the four attention heads 0 to 3 are responsible for 5-digit prediction tasks. So they are superposed because we can see that output logits of one head isn't correspond to only one digit. But even in their circuit tracing paper from March 2025, Anthropic is still suffering from this problem, and that there is no attention replacement method to discover interesting attention head structure. So the motivation of our work is clear. We put forward low-rank sparse attention, or LoRSA, to replace multi-head solver attention with an overcomplete set of sparse interpretable attention heads. And during training, we minimize MSE between LoRSA output and multi-head solver attention output, and we constrain its sparsity. This is the overall architecture of LoRSA. In the upper left figure, each LoRSA head will have an attention pattern QK, just as MHSA did. We multiply this pattern element-wise by with the rank 1 value to obtain a Z pattern. Then by summing up the Z pattern over key positions, we will get the feature activation on every query positions. The activation Z at one position is contributed by the sum of Z patterns on the key positions it attends to. For example, X3 in the figure, it has an activation value of Z. If Z2 contributes most of the activation Z, then we can say this LoRSA head activates at X3 by mainly reading from X2 corresponding to Z2 position. In this way, we can assign an interpretable meaning to it. Let's look at the example. In the figure, the width token at the query position, the y-axis, have a high activation value by mainly reading from the previous U at the key position, the x-axis. To interpret this LoRSA feature, we can also look at several signals, just like SAEs. Its activation value and its Z pattern showing which positions it mainly reads from. We can also attend to its correlated features on QKOV and its positive or negative logics we introduced before, as shown in the logic diff here. Here are some other interpretable LoRSA heads we discovered. In the upper left figure, we rediscovered previously reported attention heads that execute a specific function, such as induction LoRSA head successor, or copy suppression, and attention sync LoRSA heads. Also, using methods like path patching, we also identified arithmetic LoRSA families in Llama. For example, when computing 36 plus 62, the LoRSA head activates on the position of 36, indicates that this addend is between 27 to 43. This is the first LoRSA head. Then the second LoRSA head indicates that the addend is a mode 10 is between 4 to 6. Then the third LoRSA head shows that in mode 10 is between 6 to 8. Combining this information, we can infer that the operator 1 can only be 36. And there is a similar logic applying to 62. Then the model will do some computation to get the answer 98. We also show some quantitative metrics and found that LoRSA shows good scaling behavior like SAEs did. And we measure auto-interp scores of LoRSA, which are comparable to SAEs. Together, These results demonstrate good scalability and good interpretability of LoRSA. So let's go back to the main track of mechanistic interpretability. After understanding individual features, the second step is to connect these monosemantic features into an interpretable circuit and understand these circuits. According to the right figure, existing circuit tracing methods use cross-layer transcoders to replace MLP and use gradient-based methods to connect these features. Like the edge is the correlation of two features. And circuit tracing methods construct a linear attribution graph of features, which show the internal computation of the entire model. While only MLP is decomposed, attention remains opaque. So our solution is that by adding LoRSA to transcoders as the attention replacement corresponding to transcoders and form a complete replacement model, or we call CRM. In the CRM paper, we implement circuit tracing, which construct linear graph, just as I said before, over sparse features in both MLP and attention computations. That is why the work is called a complete replacement model. Once we have a complete replacement CRM, we can perform complete circuit tracing, and this is the algorithm. We can first unify transcoder feature, LoRSA feature, embedding logic and array node into a common encoder and decoder form. Then we need to first trace from the logic and select the first batch of important features. Then we trace from the selected features iteratively until we collect enough features of interest. After pruning, we can obtain an interactive attribution graph as shown in the bottom right figure, where each dot corresponds to a feature, a logic, or embedding, or an error. Here we show some cases here. In the first case, the prompt is Michael Jordan plays the sports off, and the model output basketball. The attribution graph shows that the model first identifies some Michael Jordan features, as shown in the left, which promotes basketball discussion feature. It encourages the output of basketball while inhibit the output of football. So maybe we can edit the model behavior by editing the behavior of basketball discussion feature and the connection between Michael Jordan feature and basketball discussions. Here are some other cases showing the mechanism of the models. On the upper left case is string indexing. The attribution graph shows an unexpected shortcut heuristic that the model often attends to salient person names rather than carefully observe the variant A that is asserted. In the graph, the key side contribution at the correct position are primarily person name features. We will expect attention to depend on assignment phenomenon on the A token because the prompt is assert A0. But the dominant path simply attends to the most salient name token. So the model may implicitly regard string indexing as being more likely to occur on person names. This may suggest a potentially fragile or unsafe behavior of the model. The bottom example is also reported in Anthropic circuit tracing work, but our feature level analysis is more granular. However, gradient-based circuit tracing methods still leave some gaps. We cannot fully expand how false statement features inhibit wrong answer like B or C, saying B or C. Then these are some evaluation metrics of our CRM. In the post, we demonstrate that our method shows good scalability, and shows good faithfulness and don't introduce much error than pure PLT graphs. We also find some fact feature sets in our lossas and transcoders. For example, the basketball or NBA feature. And several Denmark features. They have strong connections. Then next, we will move from our CRM work to the discussion of knowledge editing. We may wonder when knowledge editing meets SAEs. Can facts be edited through sparse features? And then we will first go through the two knowledge editing methods. The first one is microedit, which was published at EMMLP 2025. The idea of microedit is straightforward. They through inserting an SAE in the residual stream between two transformer blocks. Microedit can modulate then the edited knowledge during the forward pass of the original model. Specifically, we can see the B part of the figure in the left is the main architecture of its method. During training, the decoder can be trained and the encoder is frozen. And during training, SAE decoder vectors are trained through two loss functions. The first one is loss of editing, L-edit, that pushes the model closer to the targeted knowledge output, YET. While LREC preserves its reconstruction ability by keeping the reconstruction Z from changing too much. During inference, if the reconstruction error is too large, then SAE is not applied. They call it a switch mechanism or routing mechanism. The limitations of the method is clear. The first is that the routing mechanism is unstable and may not be scalable. It needs manual threshold to prevent drifting. Moreover, the method relies heavily on SAE reconstruction because the SAE will impact every forward pass of the model. So imperfect SAE reconstruction can affect the capability of the original model. Also, the paper lacks interpretability analysis, which weaken their motivation. So maybe we can do some modification upon this method. And there are the results of microedit on ZSRE datasets. And for your reference, that's the first work I introduced. And what about external editing plugins? So we don't need manual routing mechanism in the original forward pass of the model. Then I'll introduce the second one, which performs editing through external sparse features sparse circuit. We can see that this figure is quite complicated. It essentially adopts the circuit tracing or attribution graph framework of transcoders. For each prompt, it identifies the most important features, then optimize the transcoder decoders, so like adding them with the original MLP output that pushes the model towards the targeted answer. During inference, they still need a backward circuit tracing from the test prompt, which is very time costing. Then compute the J-cos similarity of the selected feature set of the test prompt VB between the features of any edited knowledge VA, any edited feature set of previous knowledge VA. If the J-cos similarity is high, then the method applies the edit by using the update decoder directions from the edited circuit. Therefore, the first limitation of the method is that it do not support batch editing, and it is slow because each edit requires separate time-consuming circuit tracing, and multiple edits are difficult to parallelize. Second, it may use unbounded memory and slow testing time because each new fact stores a feature set, leading to growing storage and retrieval overhead at test time. And here are the performance results of scan on 3 data sets. And for your information, we regard that this paper may have been rejected to ICML because its performance gains were not substantial enough, but this method still needs some it still has some inelegant design. And let's make a conclusion of the two kinds of knowledge editing combining SAE methods. There are many two ways to combine SAE with knowledge editing. The first one is integrated editing, where SAEs or transcoders modules are inserted into the base model, or a transcoder is used to replace the module. Its advantage is that it does not require extra routing. However, since it directly intervenes the model's original forward pass, it changes the original internal computation and may cause catastrophic forgetting, and it's harder to turn on or off. The second one is external editing. That is to use an external SAE as plug-in modules. Then edit the decoder of that external SAE. Its advantage is that the base model remains unchanged and it will not affect the original forward pass of the original model. While it requires extra storage and routing, and it also adds inference time complexity. Nevertheless, we remain optimistic about the feasibility of combining SAE with knowledge editing. For example, we can combine the advantage of external editing and integrated editing, like to use plug-in transcoders and tune their decoders as an external knowledge slot. We did some primary experiments, and I asked ChatGPT to draw a schematic figure of our method. And we found that we can successfully edit one prompt, as the right figure shows the demo case, which sport does LeBron James play? We added it to football, and we found prompts like what teams does LeBron James play for, and LeBron James excels at. These two prompts are successfully generalized too. We also find on different prompt templates these two features, LeBron James and Lion King or Simba feature, both activate, which shows that transcoders naturally have an advantage of interpretability, and it can help us to locate and knowledge with interpretability. However, we also found that there may be no specific SAE feature directly corresponding to some extremely rare knowledge or tokens. We call this phenomenon dark matter. Given that, I will share a background work that may provide an intuitive understanding of how SAE learn in real knowledge feature or a feature manifold. The title of the paper is Understanding Sparse Autoencoder Scaling in the Presence of Feature Manifolds. So first, we need to re-examine this thing. Like every feature in the data may not be one-dimensional. Like LeBron James is playing basketball, he sometimes needs multiple SAE latents or features to represent this knowledge. So we call these feature manifolds in the data. Let's look at some common manifolds like age, temperature, days, and so on. By reducing the model's internal activations into an observable space, we can find that some related concepts form certain manifolds, and the figure above shows some manifolds corresponding to common concepts, while some rare knowledge with lower frequency in the dataset may corresponding to a rare and low-dimensional manifold. So the paper first provides a theoretical framework for this. We first look at this figure. It's a toy model experiment. We construct the feature of data in a manifold of 2D circle, as shown in the gray circle. Then the black curve is SAE reconstructions, where we allocate specific number of SAE latents to learn this manifold. We can find that the more SAE latents we assign, the total SAE loss will keep becoming lower, and SAE latents will tile this circle into several parts, and every latent is responsible for reconstructing a single part. Further, because that there are many such manifolds in the data, we need to compare common manifold refinement and rare feature discovery. We assume that existence probability of a feature manifold follows a power law parameterized by alpha, and the loss curve of a manifold with respect to the number of SAE latents Ni is also follows a power law parameterized by beta. And after derivation, we will get if alpha is less than beta, then the number of manifolds discovered is proportional to the number of SAE latents. That means the more SAE latents we have, the more manifolds we will discover. So we may discover some very rare feature manifolds, just like some rare knowledge. However, if beta is less than alpha, it means that some feature manifolds are not common, and increasing the number of SAE latents can reduce the loss, the common manifolds by a relatively large amount. Then the discovery efficiency, dn over n, will decreases as n increases, which means that the more SAE latent we have, it will not discover it will not discover more feature manifolds. SAE is encouraged to allocate a large number of latents to the high frequency common manifolds. So the low frequency manifolds may still be ignored. In the figure, this is reflected to the red line. The discovery efficiency will be lower. Of course, in actual language models, the thing will be more complicated. The distribution pi and ln may be more complicated too, but it still gives us a theoretical instruction of how SAE will learn in manifolds, and SAE may sometimes ignore some rare feature manifolds and repeatedly learn some common feature manifolds. We are also exploring some techniques like oversampling as a way to increase the occurrence probability of certain data, which makes it easier for SAE to learn some rare knowledge than to have a powerful effect on knowledge editing. Finally, I would like to thank our advisor, Professor Xipeng Qiu, our mentor Zhengfu He, our collaborators, and our labs for their guidance and support. And we welcome everyone to refer to or cite our work. And we are also welcome to cite other related papers and use our code repositories. That's all for my today's talk. Thank you. Do you have any questions?
Yeah, hello. Could you please come back to slides when you discuss knowledge editing procedure?
Knowledge editing procedure, yeah.
Yeah.
Do you mean this slide?
I guess next one.
Next one.
I guess next one. No, previous. When it was a graph.
Yeah.
Could you please repeat the intuition of the procedure? Where is the graph? What you do with the graph? We understand that you provide external procedure when you change something in SAE and just adds the SAE outputs to outputs of the model layers. But what do you do in SAE? Could you please repeat this one?
Our motivation is based on is mainly from we use transcoder encoders as sparse feature routers. Then we train the transcoder decoders because the transcoder is plugged in the external of the model. It will not harm the original model forward pass. And also, the encoders already provides an interpretable sparse feature routing mechanism. So we can, for example, if the prompt is which sport does LeBron James play, we'll find that in many different prompt templates, the LeBron James feature always activates, and then we added the decoder of its feature to steer the model to encourage it to say football. So this is our motivation of the method.
Yeah, okay, thank you. And I guess I have one more question. What about overfitting? Because in knowledge editing, there is some overfitting paradigms. For example, if we provide locate and edit methods, make locate and edit methods, we overfit directly to a new object of the triple. But maybe you discover and research your procedure in case in terms of overfitting to some facts.
Um, Excuse me, do you can you repeat your question because I didn't understand it. I'm sorry. Do you mean
Yeah, of course,
overfitting?
of course.
Yeah.
Yeah. I mean, overfitting. I can give you an example. For example, we would like to change that LeBron James play not basketball but football, and if we do just plain locate and edit procedures such as roam, mimit, and other procedures, we just overfit to this fact. In the procedure, we give the model a lot of prompts and we plainly overfit the model output to the answer that we want, so football. So what about your procedure? Do you see such effects in your method of KIA knowledge editing?
Yeah, good question. I think our methods, our position will not suffer from overfitting in that so much because in different knowledge or different facts, the original parts of the model will not change. So the basic capability of the model is preserved. While if the model detect that it's a prompt about LeBron James, so it will activate the LeBron James feature. Or in other prompts, you will not activate the LeBron James feature. So if it detects LeBron James, it will activate the LeBron James feature and encourage to say football. But in other original prompt, the original forward pass will preserved. So I think our method is a good that can prevent overfitting.
Yeah, and one more question. How many layers do you replace with transcoder during the knowledge editing procedure?
Yeah. Good question. We are still trying. We can do some same setting as Mammoth or Alpha Edit, like because like we train transcoders on layer 13 to 17 or Llama. We found that the overhead of training transcoder is very high. So we won't train transcoders on every layers. I think some middle layer of the model is enough.
How do you trace the layer that should be edited? Do you use procedure like causal tracing from ROM, or is there some maybe another more modern procedure?
We are still exploring this problem. In the first version of our method, we follow the setting of Mammoth that to use layer 13 to 17 of Llama. Yeah, we follow the previous settings.
Okay, thank you.
And what about how do you find the sparse features that correspond to the fact that we need to edit?
We can use different prompt templates, like which sport does LeBron James play? What does LeBron James play? LeBron James play 点点点, for example. And we sample many prompts and find the same feature they both activates on the subject token, like on James. So we identify it is a LeBron James feature and edit
thank
it.
you.
Thank you. In the first part of your speech, you talked about replacement model for attention layers, but in the knowledge editing setting, you only use like NLP layers. Did you try to перенести?
Ну, to apply,
Перенести.
transform.
Transform knowledge editing procedure to like maybe attention layers, maybe use some sparse features from Lorsa or something like that.
I think we can also try to use sparse features like Losa and combining it with transcoders. But the previous work mainly focused on MLP layers. They mainly added MLP layers. So we want to first to make our precision work by training decoders, and then we will further integrate Losa into this precision.
Yeah, thank you.
Thank you for your presentation. I have also one question. Do you somehow extrapolate your research on MOE architectures? Because Llama 3.1 is a dense architecture, and recently MOE architecture of models is more preferable for different practical tasks.
It's a good question, and that's the third direction we will try to, because the Losa, the method combining Losa and transcoder is the first attempt. So we didn't try it on MOE architectures, but I think with some proper modification, it will still works, because we think the sparsity hypothesis or the superposition hypothesis is still work on MOE architecture models.
I understand. Thank you. And how does the superposition theorem works for MOE? Because you know that there are experts that have more preference compared to others in final output of the model, and I think the naive implementation of the superposition wouldn't work in the same way as in the dense model.
Yeah,
you
your
have a
point
specification of experts.
is a good point. But we argue that the feature on the data are much more than the MOE experts, the number of MOE experts, and some MOE experts still need to process data in a superposed way. They are responsible for more feature of data, and maybe we can try it out, but yeah, it still remains the gap that the sparse replacement methods are still blank in MOE architecture. Thank you for pointing it out.
Okay, thank you. I'm waiting for further research in this area.
Thank you.
Yeah, one more question. Could you please specify how do you train the decoder, interscoder when we speak about knowledge editing?
We first train transcoder as the former as the previous baseline, or we train transcoder to approximate the MLP input and output of the original model. Then we set its decoder to 0, and we insert and then we plug this transcoder beside the MLP layer, and just like Mammoth or other methods did, we still firstly optimize the output vector V, then compute the feature decoder of our additive features, our selective features, to meet the V.
Just to verify, am I right that you just make a mimic procedure and after that you train transcoder?
Do you mean that our pipeline of training transcoder?
Can you repeat?
Is your question about our pipeline of how do we train a transcoder?
Yeah.
Or-
This is my question. This is
Okay.
my question in the knowledge editing procedure. Am I right that you make editing procedure like Mimit, ROM, etc. And after that, after you make this procedure, you train transcoder on new outputs of the model?
We first train transcoder on the original input and output of the model of a MLP module, and we store the activation of some tokens, some data, some MLP input activations, and transcoder takes in MLP input and approximates MLP output. We just sample some random data to train this transcoder. We do not use knowledge editing method to train the original transcoder.
Yeah. Okay, thank you.
Hello, can I ask a question? Maybe a similar one, but when you assign a feature to a subject, shouldn't you do it vice versa? So, for example, like in Anthropic's blog post, where they sample top 20 top 20 prompts with the highest feature activation, and then assign subject to the feature and not vice versa. So for example, you can overfit and edit model knowledge to answer particular prompt, particular answer to any James, not only LeBron James.
Yeah. This is a good question. But because we when editing a knowledge, we do not only sample one feature. We may sample the top 10 features, and when combining them, the model will know the input is LeBron James or any James, like James Harden. I think it's a trick. It's a engineering detail that we can select the number of features to prevent the model to overfit to any James. Yeah.
Mhm.
Yeah. What kind of models do you use for experiments?
We first use GPT-2.
Sorry,
Actor.
did you try some models that can perform multi-hop reasoning, and did you compare with methods like CODE or some other modern methods for reasoning models? Because we think that the use of SAE can help to increase multi-hop performance of models. Did
Yeah,
you
yeah.
validate on benchmarks like Quake or something else?
Yeah, I think this is a good point. But now we didn't use SAEs to knowledge to edit some multi-hop knowledge because I think we should first focus on the basic knowledge. So to some base knowledge, because SAE still has dark matter. It sometimes may suffer from some real knowledge too. So if we don't answer this problem to tackle this problem, the interpretability of our methods or the white box heart of our methods will be weakened. But maybe we can still collaborate on some multi-hop knowledge editing scenarios. Yeah. Thank you.
Yeah, thank you. Thank you for, I think it's a good point. It's a good point because modern models always perform reasoning. So knowledge editing procedure should be adapted for reasoning models. Yeah.
Thank you for the presentation. I also have a question. You have mentioned the nonlinear representations, which are different from the standard SAE linear ones. Can you please switch to the slide where the black and gray circle appear?
Do you mean manifold? Do you mean this?
Yes, I mean manifolds. Yeah, thank you. And my question is how the knowledge editing procedure transfers to this case, because in the linear case, everything seems clear how the intervention in the feature direction can be conducted. But in a nonlinear case, it seems a bit unclear to me how to make the adjustments in some manifold directions.
Yeah. This is a good question. I think the nonlinear manifold can be approximated by the combination of some linear SAE feature directions. Like in this figure, we can use 24 linear feature to approximate this nonlinear manifold. So combining to knowledge editing, if we select the more SAE features we added, then we will have an effect like we actually doing some editing on a manifold. So just as I said before, the number of features selected is more than one. So like we can select 10 features to edit for one knowledge, and it actually serves as an approximation of this feature manifold of this knowledge.
Okay, thank you.
Hi, thank you also for your talk. I have a question about the number of tokens required to train one Lorsa layer. I guess the rate to the number of parameters in one layer.
We train a Lorsa layer with about 800 million tokens activations.
Okay, and what's the number of parameters in that Lorsa layer?
The parameter, the number of parameter is due to the expansion factor we selected. If we select the expansion factor like 8, then the number of Lorsa heads will be A plus the dimension of dimension of model. So it will be the dimension of multi-head self-attention heads. It will be the number of Lorsa heads over the dimension of multi-head self-attention heads plus the original multi-head self-attention parameters.
Yeah, I know. I mean, what's the rate, maybe the rate of the number of tokens required to the number of parameters trained? Because, for example, when we train sparse autoencoder, we replace for each feedforward network, we train one sparse autoencoder. They are approximately equal in the number of parameters. Even one sparse autoencoder is 1.5 times less parameters, because we have like up gate and down projections, and in sparse autoencoders we have only like up encoder and down encoder. And that means that if we train like Llama 3.18b, we have approximately 5 or 6 B parameters in feedforward network, and we train approximately 3 or 4 billion parameters for sparse autoencoders. But if we want to train something for multi-head attention, for example, Lorsa, we have to train 8 times parameter that we have in multi-head attention. For example, for multi-head attention, we have 2 billion parameters. It means that we have to train like 16 billion parameters for Lorsa. Am I right?
Yeah, you are right. But actually the number of parameters of Lorsa and SAEs are similar, because we can regard Lorsa as an encoder like WV and a decoder WO. And we set the number of training tokens similar to SAE, because we found that after 800 million tokens of training, you will have a similar convergence like SAEs did.
Yeah, okay, that's actually nice. But still, like, we have to train so many parameters, and I guess it is very time-consuming procedure for this kind of layer. So we have like the compute bottleneck here. For example, I think if we want to train the entire SAE plus LORSA for entire llama, we need approximately 2 months of GPU hours.
I think for one layer, maybe we can we may use H100 cards, and we use 4 to 5 hours to train one layer of SAE or LORSA.
Yeah, but if we like want it for the entire model and we want both SAE and LORSA, we have like months, but it's actually a bottleneck here. But yeah, still just an interesting. Thank you very much.
Thank you. You are right. We will not easily to understand a model with a cheap method. Yeah.
Guys, do you have any questions? Okay, so Rui, maybe we can go to another meeting, another conference, and we can discuss our potential mutual projects. Yeah.
Thank you.
Thank you.
Yeah. So I think Dima, you covered also a bit.
Yeah,
Yeah,
thank you.
thank you.
Then let's welcome
Thank you.
Wang.
Okay, thank you very much. I will share my slides. Okay, thank you very much, and thank you for the invitation and a wonderful presentation from Lin Rui. And I will present my my work. Sorry. I will present my my work titled Diagnosing and Mitigating Evidence Misgrounding in Multimodal Knowledge Editing, which is submitted to EMNLP 2026. Oh, let me start with introduction of knowledge editing. I think most of you may be well familiar with the background. Just give a brief introduction of multimodal knowledge editing. Trained neural networks store a large amount of factual knowledge. However, the knowledge can become outdated or may simply be incorrect, for example. And in the right part, there is a specific example of a multimodal knowledge editing. There is a VQA sample of the prediction of the current president of the which is outdated and needs to be updated. One straightforward solution is retraining or full fine-tuning, but retraining is expensive and fine-tuning leads to overfitting and poor generalization performance. Knowledge editing is designed to as a more targeted alternative. The goal is to update a specific fact efficiently and while preserving unrelated knowledge. In multimodal knowledge editing, there are similar evaluation metrics as text-only knowledge editing. For example, reliability, locality, and generality. But there is a question: are these metrics enough for evaluating a good multimodal knowledge editor? Our answer is no. Our answer is no. Let me introduce a new concept named editing evidence. In text-only editing, the evidence is usually explicit in the text. For example, if the query asks whether Joe Biden is a current president of the United States, and the relevant entity and the relation are directly expressed in language. However, in multimodal knowledge editing, this situation is different. An image contains intended visual evidence, but also contains many contextual features that may be irrelevant. For example, in the question, the bottom questions in this picture, we ask how many skyscrapers are there, but the skyscrapers actually located in a very small regions of the picture, while there are many contextual attributes such as boats, trees, sky, and the river and people. Another example is that the prediction of the bird habitat. For example, if we ask the model, is this bird a land bird or water bird? We expect the model to attend to the bird features instead of abundant background noises. So this is a problem with physics. So we introduce we call this finite mode evidence misgrounding, which means apparent edit success can mask sensitivity to incidental visual context rather than stable alignment with intended evidence. For example, in this picture, the edited model may remain successful on the original edit sample, but when the background change, the edited model cannot generalize well to the similar image. So it cannot generalize well when background shifts. So this is a bad phenomenon. So to study this problem in a controlled way, we construct a diagnostic set called waterbird edit, on which we perform lifelong editing. The construction starts from the cube bird dataset. We formulate a binary visual question answering task. For example, given a bird image, the model needs to answer whether the bird a land bird or water bird. Then we filter samples where the original multi-language model makes an incorrect prediction. These error samples become editing instances. As the edit target is a correct habitat level for each edit, we construct the standard evaluation types: reliability, text generality, image generality, text locality, and image locality. The final waterbird set allows us to evaluate lifelong editing while also explicitly testing whether the edited model follows the bird evidence or the background context. The key design of the waterbird edit is that it separates two visual factors. The first factor is the intended evidence, the bird type, the bird habitat type, water bird or land bird. The second factor is incidental context, the background, the land or the water. Combining this gives four target context groups: waterbird with water background, waterbird with land background, landbird with land background, and landbird with water background. This design is useful because the groups are naturally imbalanced. In many images, water birds are more likely to appear near water, and land birds are more likely to appear on land. This creates a spurious correlation that the editor may exploit. So the diagnostic question is, after lifelong editing, can current editors still generate while when the background shifts? If a model has really learned the edited bird fact, it should follow the bird evidence across backgrounds. If it relies on the background, performance will drop in a specific data groups. So we further conduct a series of experiments. To qualify this behavior, we report 3 main metrics on waterbird edit. The first is the standard image generality. This is the average accuracy on image reference samples. The second one is group-wise image generality. Instead of reporting on the average, the overall image generality, we compute image generality separately for each target context group as listed below this question, this formula. This tells us whether performance is inconsistent across background conditions. The third one is performance gap. We define it as the overall image generality minus the worst group image generality, as shown as this. A large performance gap means that the model performs well on average, but falls badly at least one group. In this setting, a large performance gap indicates a sensitivity to incidental background context. The bottom is a table of our results. We compare 2 representative baselines. The first one is fine-tuning, which update model parameters, and live-weighted, which modulate hidden states. Live-weighted is a current SOTA work of multimodal knowledge editing that is published on CPPR 22.5. As to the results, both baselines can improve answer level performance, but neither explicitly separate target evidence from background context. As we can see, they both achieve the lowest performance across in some specific data group, and shows very large performances. So this is what we find, and we further mask the background to diagnose if the background what the effect does the background show. So if we mask the background and report the overall image generality, the metric improves across the 2 baselines, which means that the background degrades the generalization performance after the editing. So this is what we find, and we also conduct one more experiment. We also inspect model at the sample-wise probability level. We propose a new metric called sample-wise normalized probability assigned to the water answer among the two candidate answers, water or land. The S water means model logic of the prediction water. The S land means model logic of the prediction land. So this metric shows intent the model tries to predict water. So in this image, we can see that the first two baselines shows a large gap between some between some groups. For example, the first two rows corresponds to the water bird with different background types. However, when background change, the probability shows a large gap, so as to the live shows a similar behavior in the bottom two rows. This is what we find. So we conclude two findings. The first one is current knowledge editors are not robust to target context shifts. Their apparent image generalization is not robust under change in the incidental background context. And the second one is object-only masking disentangles the effect of the background context, as we discussed before. So motivated by this diagnosis, we propose VICE, or visual in context editing. VICE is based on 4 design choices. First, it keeps the multimodal large language model frozen. This avoids damaging unrelated knowledge and avoids inserting new spurious correlation through parameter updates. Second, it uses evidence summary demonstrations. These demonstrations explicitly describe the task-relevant visual evidence and separate it from incidental context. Third, it introduces a sequence memory to support lifelong editing, and finally, we introduce a similar-based retriever with a learned scope discriminated head. At inference time, the retriever finds the most relevant stored, edit, and construct an augmented prompt only when the query is judged to be in scope. So this is the overview of our proposed method, VICE. Let me introduce a preliminary of in-context learning and in-context knowledge editing. In-context learning actually provides many pairs of demonstrations as shown as this. Each pair of demonstrations is a pair of a question and answer if we face a QA task. The model learns from these demonstrations and learns the relationship between X and Y and try to apply it to the new query. So this is in-context learning. The in-context knowledge editing applies in-context learning in a similar way. For example, we have also a sequence of editing demonstrations. However, each of these demonstrations is as is the template. We insert the new fact and we have a prompt. Note that the new fact has no relation with our truly edited new fact. It's an example, or it's a template that the model can learn some relationship between the new fact and the prompt that can be used to further to the future new fact. So this is in context knowledge editing. In the right part, we have an example. For example, if we have a new fact that to be edited, the fact is we edited the model output of the country of the Paris from France to Japan, and we have a query question. For example, which city is the capital of Japan? We expect the model to answer Paris. But how can model know what we expect it to do? It learns from the previous context or demonstrations. For example, we have a new fact, but this new fact is sampled from training set. For example, there is a new fact. The president of US is we correct the answer from Obama to Biden, and when we face a new query, for example, the president of US is the same of the original new fact question, it should answer with Biden, or we have a semantically similar question in this example, should also output the corrected answer. Or if we have an unrelated question, it should maintain the prediction. So this is what demonstrations do in context knowledge editing. So VICE, our proposed method, builds on in context learning and in context knowledge editing. But there is a question. There is a question how to perform visual in context knowledge editing, and how to demonstrate visual context. A straightforward way is to input iterative image text pairs, but not all models support this format, and the large number of image tokens can significantly increase the inference burden. Alternatively, we can convert image side context to textual image summaries, or we call it evidence summary demonstrations, as this template. We just insert a prefix named image summary, and the image summary is obtained by pre-trained multimodal large language models, and which can be the multi-language model to be edited. We construct five types of demonstrations for different roles. This is the similar way as what IKE did. This is 5 types of visual demonstrations. For example, copy, text update, image update, text retain, and image retain. And how to perform lifelong visual in context knowledge editing. A straightforward solution is to use all edited facts as context input, but it leads to an infinitely growing context window. So thus we induce memory retrieval mechanism, which just stores incoming edits in a sequence memory, and during inference we retrieve retrieves from this sequence memory and retrieves the most relevant edited fact based on the similarity computed by a deep vision language encoder and a learned scope hat. Yes, as shown in the C part of the image of the pipeline. Why we insert why we append a learnable scope header after the deep vision language encoder? Because if we use the original deep vision language encoder, the similarity cannot be separated well across this evaluation data groups. For example, if we set the if we use an image locality sample to retrieve the most similar edit factor, it may give us a very high similarity, which may be incorrectly judged as in-scope knowledge. So we use we insert learnable scope discriminated head and train it in the of the training set, and we use two losses. One is retrieval loss and another is margin loss. The retrieval loss pushes the in-scope knowledge together, and the margin loss pushes the out-of-scope knowledge away from any other in-scope knowledge, edited knowledge. So this is the pipeline of our proposed visual in-context knowledge, in-context editing method. This is the experiment part. First, we conduct diagnostic experiments on our proposed waterbird edit. As we can see, VSCE achieves a lowest performance gap and achieves the lowest gap between the normalized prediction probability. We also conduct experiments across three standard knowledge edit multimodal knowledge editing benchmarks: EVQA, EIC, VLKEB, and we use backbones Lava v1.5 and MiniGPT-4, and we conduct lifelong editing. Across these benchmarks and backbones, we achieve a very considerable performance, overall performance, and the one point is we can look at the image generality. We improve very great compared with previous work. For example, we improved about 10 points compared to the live edit, and yes, it's a very big improvement, and we remain high performance across reliability and locality, but the performance of text generality is suboptimal. And another point is that when we increase the total number of editing samples to perform lifelong editing, our performance remains stable. However, at other baselines, the performance of other baselines drops greatly. Yes, this is this table reflects the experiment result across three benchmarks and with the backbone Lava. This is experiment plus 3 benchmarks and with backbone mini GPT-4 with the same conclusion. We also conduct application studies to show the role of the different parts of our method. This is overall result. For example, if we drop the context or demonstrations, performance drops greatly. And we also sweep the threshold theta on EBQA and with the backbone lava. We can see a apparent trade-off between generality and locality. If we set the similarity to 0.65, we can achieve a considerable overall performance across 5 metrics. So this is our proposed visual in context knowledge editing method. Thank you.
Thank you for the presentation. I have a question. Could you please go back to the slide with preliminary results where you compare the performance of fine-tuning, live edits, Weiss on inputs with and without masked background? Yeah, thank you.
Background, masked background. Do you
Previous
mean
slide.
this table?
It was in the beginning. Yeah. Maybe I didn't catch something in your method, but how do you explain that Weiss, your scheme, loses quality when you mask background of the objects, and for fine-tuning and live edit, the quality increases?
This is a good question. We can see that when we mask the background, the performance of the first 2 baselines improves, which means that actually did a negative effect after the editing. While for our proposed method VSE, when we mask the background, the performance drop. It's reasonable. It's reasonable because the model actually learns a shortcut in the background. But when the first 2 baselines trains the model on our proposed waterbird edit benchmark, it learns a shortcut in a strong extent, but our method did not shows this behavior.
Yeah, I understand. Thank you.
And could you return to the slide with your method?
Oh yeah.
Yeah, thanks. I have a question. I did not catch you did not edit the base model, yeah? You just create a little bit more context before the inference.
Yes.
Okay, thanks.
Yes, the question
Yes,
the question is what's the format of the model input? You just input the query to the model MLM, and in the slides in the subsection C, you provide some edit retriever, etc. And what is the format of input of these edits?
for the format of the input, you mean the final augmented input to the model?
Could you please repeat?
Oh, we actually the final formation of the augmented prompt is many. Yes, we can look at this picture. The final form of the augmented prompt is we just put the context as a prefix to the query.
Okay, thanks. And how do you train the scope head? I mean, what the main idea of this? I didn't catch it.
Oh, the training of the scope head is motivated by this experiment. We find that if we use the original clip encoder, the output features cannot be separated well across in-scope knowledge and out-of-scope facts. So we train an external scope discriminated head to improve to separate the in-scope knowledge and the out-of-scope knowledge well.
Okay, thanks. Yeah, understand.
Thank you for your questions. Do you have any question?
It seems like it seems like no. Yeah, thank you for the presentation.
Thank you. Let me stop there.
So I guess we finish. We can discuss further steps in the chat. Yeah, about mutual collaboration. Yeah, again, thank you very much for the presentation. It was very, very helpful and interesting.
Thank you for presentation. Have a good day.
Yeah, thanks a lot.
Yeah.